So I'll get started. I'm going to start with sort of the standard polling of the audience. How many people have heard of Apache Mesos? All right. How many people use Apache Mesos? OK, handful. Great. OK, awesome. So it's great to be here. It's my first time in Philadelphia. I got in Sunday, and so it was beautiful. Sunday and Monday were really gorgeous days, and nice to be here. OK. So I'm going to be talking about building and running distributed systems with Apache Mesos. I'll start off real quick with a who am I? So I was a PhD student at Berkeley. That's where Mesos actually came from. It was PhD work with myself and some other students. Then I went to Twitter. Twitter started using Mesos in about early 2010. I was there for quite a while. And more recently, I've helped to found a company called Mesosphere, which is commercializing Mesos. So I'm here, and maybe we're all here, because the other computers that we use, my other computer, is really a data center. And when I say data center here, really what I mean is a collection of machines, whether that's a bunch of virtual machines that you're getting provisioned from the cloud, or whether it's a bunch of physical machines that you have in some colo space or your own private data center. Whatever it is, my other computer is a data center. And I really want to treat all those other machines like one big machine, like one big data center computer. And some of the questions that I'm going to try to address in this talk are, first, how should we really run applications on this data center computer? What's the best way to actually run our applications? The second is, how should we program our applications for something like a data center computer? And I guess we'll start with, and what's most important, which is, what are data center applications? What even are these things? What actually am I talking about? So that's going to be the agenda. That's what I'm going to cover for the next, we'll say 40, 45 minutes, and then break and let you guys ask a bunch of questions. OK, so diving right in. What are data center applications? What do I mean when I say data center applications? I mean distributed systems. That's really what I'm talking about. But there's different classes of distributed systems, so I kind of want to break this down so that we can really understand the space of what's happening in the cloud and with cluster management and orchestration and all these things, OK? So when you typically hear the word distributed system, a lot of people think of a couple things. One, they think of people that have PhDs are only the ones that are building distributed systems. The other thing you often think of is a collection of stuff that looks something like this. So these are the standard distributed systems that lots of folks think of. And there's probably others that are not on the slide. I'd love for people to come afterwards and tell me, hey, you should really put that distributed system on the slide, because that's the one I think of, OK? Things like Hadoop, Cassandra, HDFS, Kafka, Elasticsearch, Memcache, HBase. The lightning bolt is for Storm. I still don't think Storm has a logo. I don't know if that's true or not. Accumulo, Spark, and others, OK? And I'm already going to kind of group these two classes of distributed systems in two different ways, because it actually becomes really interesting later when we talk about what it means to actually program and run distributed systems. And the two groupings I'm going to quickly do is between stateless and stateful distributed systems, where stateless are things where they don't care necessarily about the machines where they're running on. They're not writing any state to those individual machines. And stateful means they typically are writing data to disks on those actual machines, OK? So I'm already going to do that. But there's another large class of distributed systems that I spent a lot of time working on, and I'm sure many of you have also spent a lot of time working on, that don't typically fit the bill when people think, oh, distributed system. And that's the distributed systems that most of us are building at our respective companies, OK? So the company that I'm going to pick on is Twitter. And this is basically a very small subset of the distributed system that makes up Twitter. Okay? So it's a whole bunch of different services that are all connected together and communicating with one another to actually achieve some service or provide some product. Okay? And oftentimes when we think about these distributed systems, the names that come to mind are things like service-oriented architecture, more recently the term microservice. But in general, there's just a whole bunch of services that compose together make up some bigger service. So this is not a talk that's about microservices, but just a few notes about this, because Twitter actually migrated from a monolithic world to a microservices world. And we did it for a couple reasons. One, because when we moved to a services world, and I'm going to keep saying we, but I'm no longer at Twitter, so they. When Twitter actually moved to that world, they wanted to move to a world with microservices because they wanted to be able to do one thing and do it well, kind of the Unix philosophy. A bunch of little things that did one thing and does it well. Because you can compose these things, because you can build and commit in isolation. You can test these things in isolation, you can deploy in isolation, you can easily roll back in isolation. And it ends up capturing the organizational structure of many teams working in parallel and actually doing things at the same time. Okay? So what's interesting though is even before Twitter migrated from a monolithic architecture to a microservices architecture, this was kind of the Twitter monolithic architecture. It was a large Ruby on Rails application that was affectionately dubbed the monorail. It was still a distributed system. It was still a distributed system because it was running on lots of different machines, and a lot of the other components that it was communicating with were still distributed, especially all the storage components. There was still some notion of distribution of how things were actually working. So I think one of the really interesting lessons here is that no matter what, there's just really no getting around it. Everybody, for the most part, everything that we're working on is effectively a distributed system. If you're working in the cloud, if you're working on a mobile app, it's still distributed. It's going from your phone to other places. Everything at the end of the day is really a distributed system. Okay? And this actually is not, this is actually a title of an article that I highly recommend you read. The slides will be available, so you can check that out. Okay? So in the article, the distributed service, the distributed system that they give, the example is this. It's an image resize service, and it's made up of a couple different components. There's an authentication cache. There's an API server. There's a usage server. There's an identity server. And then there's the actual image resizing components themselves. Right? A whole bunch of different components that are being composed together to actually provide this image resize service. Okay? And when you look at a picture like this, as a distributed system, it really doesn't look too much different than one of the distributed systems that we might think of more generally, something like HDFS. This is kind of a very high-level diagram of what HDFS looks like as a distributed system. Something like Spark, if you've ever worked with Spark. This is actually an interesting one. This is what you'd consider a very composed distributed systems. There are many sub-distributed systems that make up this whole thing: Kafka, Storm, HBase, so forth and so on. Okay? So when I talk about distributed systems, data center applications, I'm really talking about both the things that somebody might build initially as a distributed system, like a Kafka, like an HDFS, like a Hadoop, like a Spark, and also just the things that people are working on themselves, a bunch of microservices that you're composing together to actually construct some service for your organization. Okay. So that's what I mean by what are data center applications. Now the next question, as we start to get into the meat of it, is how should we actually run these data center applications? Okay? And there's a couple considerations that we need to think about immediately when we start thinking about how we want to run our data center applications. And the three things that I really think are the most important to think about are configuration and package management, how to do deployment of the actual services that you're trying to run, and then how to actually do service discovery of the things that want to be able to communicate back and forth with one another. So there's a fourth one, which is actually really, really critical, but I'm not going to cover it in any depth today, and that's really how to do monitoring. Okay? And that's really how to actually monitor all these components that you're actually running. Okay? So the people that tend to take care of a lot of these pieces are the ops folks, the ops guys, right? And I think what's really interesting about this is they tend to need to work in coordination with the devs. Both are grumpy. And there's this interesting parallel and play between those two, and I'm going to come back to that throughout my talk. Okay? So, and to be very clear, these are not hard and fast considerations. A lot of these things overlap. Some of the issues around configuration, package management have to do with deployment, have to do with service discovery, so forth and so on. Okay? So I just want to dive in when I'm mentioning these considerations, what do I really mean? So for configuration and package management, I'm really talking about the what and the how of the way things get installed, of how the bits get to the individual resources so that computations can run. Okay? So when you're in the tens of machines world, you can often get away with things like having a host.txt and doing a bunch of SSH to actually do the configuration package management that you need to do across your tens of machines. Okay? That's kind of the world you can live in when it comes to configuration package management. Okay, maybe you don't just copy bits. Maybe use things like RPMs or other packages. Okay, the next step is really deployment, and the deployment question is really what should run where, and how should those things be started and stopped. Okay, so again, if you're in the tens of machines world, operators can say, okay, I've got this collection of machines, and I'm going to go ahead and I'm just going to SSH these machines, and I'm going to launch my applications. Okay, maybe I just use no-hop, maybe I use monet to actually launch these things so that if they fail, they can get restarted. Maybe I use some collection of this. Maybe I copy my bits. Maybe I end up using git to pull down my bits. Okay. Okay. And then finally, for service discovery, it's really how should the individual apps, how should the individual services actually be able to find one another, okay? And again, if you're in the tens of machines world and you have a whole bunch of your different text files, which is representing all the different the machines you're actually working with, you can go ahead and you can just manually configure, and you can say, these machines are being used for running this application, so here's how you find the other guys. This machine is being used for running these applications, so here's how you actually find these guys, okay? And this might all work, these techniques might all work in the tens of machines, but as we start to scale, even in the tens of machines, it starts to break down. And as we start to scale, we need less moving parts, and we need a lot more automation as we go from the tens of machines to the hundreds of machines to the thousands of machines, okay? So Twitter, circa about 2010, was in this world of machine hosts, text files, using things like Puppet for configuration and package management, Capistrano for deployment. So I kind of want to take you through the story of what it looked like at Twitter to actually do, what it actually looked like to run these data center applications in a Twitter data center, and how that actually evolved. Okay, so this is circa 2010. So it started something like this. There were a whole bunch of machines, and we needed to then go ahead and decide what machines were actually going to run what applications. Okay, so a human did this. A human actually said, all right, I'm going to collect this collection of machines, and I'm going to say, these machines are being used for run MySQL. Okay, or a collection of humans did this, some body of people. How many people actually attended the Kubernetes talk earlier today? Yeah, I really liked it when Kelsey described the collection of people that were doing this scheduling as the meat cloud. Which was, it's great. I got to find Kelsey and tell him that like his joke got 2 laughs in 2 different presentations. Okay, so there's a collection of humans that are actually deciding how they want to schedule these different services that you're trying to run across a collection of machines. Okay, so they say we're going to use these machines to run MySQL. We'll use these other machines to run Memcache. We'll use these other collection of machines to run Rails. Some to run Cassandra. Some to run Hadoop. Okay. And now we start to get into a bunch of challenges, all right? So the first challenges that we really run into is what happens when failures occur, okay? So this is actually a real email from Twitter where I've scrubbed most of the names. Abdur was the chief scientist at the time. Roger Rabbit did not work at Twitter. Okay, what the email says, it says, hey, so this box had to be rebooted. Were there any production services running on this machine? It's a real email, right? So this is what happens when this is the state of the world, and a human has actually gone through and said, yeah, this is the machine I'm going to use to actually run this. The machine has to get rebooted for whatever reason. And people are like, wow, what impact has that actually caused to my operations? Okay? So what does that look like? It looks like this. Some machines are being rebooted or failing or whatever's happening all the time. Okay? And again, as we move from tens to hundreds to thousands, this becomes a very, very frequent event. Okay? The types of failures that this meat cloud really has to think about is not just machine failures, but also failures at the rack level, failures at the switch level, failures at the entire data center level. So there's actually a lot of things that are going on there that somebody needs to think about. And all this stuff applies to the cloud as well. To machines, instead of racks, you have zones, and instead of data centers, you have regions, or whatever the alternative word is in the different clouds. Okay? So the second challenge that people really have to deal with is maintenance, and what I like to call planned failures. Because effectively, when you're doing maintenance, you're inducing a failure in the system. You just know when you're going to induce that failure. Okay, so you can prepare for it. Okay, so it's planned. All right. So maintenance is especially tricky between the operators and the developers, because operators need to do these things either for security updates, performance improvements, whatever it is, and developers tend to not want to have to deal with the fact that there's going to be some downtime for their service that's running someplace, right? So typical example of maintenance is upgrading software, in this case, something like the kernel, okay? The other big maintenance, though, is actually replacing physical things, whether it be machines, racks, entire data centers, okay? So what does that look like? Well, I deliberately set up this graphic so that unfortunately somebody from the Meat Cloud had done a poor scheduling job here, and we decided to do some maintenance on the rack that is running all of the mem caches, and in this case, all the mem caches are down. And in a circumstance like this, a service like Twitter would definitely not be operating. There's far too much load to ever be able to hit the databases directly. Okay, and then finally, the last challenge is utilization. So if you go back and you look at each of those static partitions, you'll realize that the amount of resources that are actually being consumed in each of those partitions varies throughout the day. So if we just take 3 of them, Rails, Hadoop, and Memcache, Rails definitely has a diurnal cycle. When the sun is in the middle of the Pacific Ocean, less people are tweeting. There are less resources that are needed to actually serve the users. Hadoop might scale up at arbitrary times, especially at night, because we need to collect things like Gartner reports for who's watching what shows and retweeting what things. And then Memcache probably follows something pretty similar to Rails, okay? Except for that big spike at the end where, I don't know, say somebody famous tweeted, I know what you're thinking, but the famous person is Justin Bieber. He's a famous person that tweeted, yeah. So, so what we'd really like to do is to be able to leverage all the available resources across this period of time, and be able to get higher utilization and run our jobs faster, right? So that's really what this other graph is showing, is if we could use all these resources that's available, instead of statically partitioning a third of the resources into each of the systems, we can have 100% and one individual service can scale to that 100%. Then ultimately we could buy less machines, we could buy less resources, or we could run more applications, okay? And in most circumstances, you just run more applications because people just keep buying machines. Yeah, I recently gave a talk at Intel, and I was chatting specifically with Intel, and they were saying, oh my gosh, running less applications, buying less machines, that's horrible, right? Our business is going to go down. But that's never seemed to happen. Even with virtual machines, if you look back at the industry, the hardware industry was just as worried about virtual machines at that period of time, and guess what? People continued to buy lots and lots of machines. So people just run more applications. That's what ends up happening, okay? So if we kind of look at the challenges, you think about sort of how do you plan for things like failure and maintenance? What's the human side of this that actually has to occur? Human needs to think, the operator needs to think, how do I plan for failure? And that ends up looking something like this. So this is another real email from Twitter, and someone saying, hey, we're trying to set up a couple of database masters, and we'd like to know which rack switch and PDU these devices are on. Why? Because preferably they're on different racks, switches, and power feeds so that they're fully redundant. Right? Again, this is a human that's actually doing this data center scheduling to figure out how they should run their applications in the data center. Okay? And then on the utilization side, again, you'd have to plan for this kind of utilization. And there's really 2 types of utilization you really want to care about. One is sort of this intra-machine utilization, which is to say, even on a single machine, if you're buying, say, 16 core machines with 32 gigs, what's the best way that you can fully take advantage of that machine? Whether it's a machine you got from the cloud, or whether it's a machine that is an actual physical machine. And this is a really tricky one, because for most people out there today, even though they're using cloud resources, they're still not effectively using their cloud resources. The people that are really benefiting from the cloud are the cloud operators themselves. Okay? And the other thing you really want to care about is sort of this intra-data center resource sharing, or across machines resource sharing, which is how can I actually move resources around so that certain services can get more resources from other machines, or less resources from machines, depending on the actual load that they have on their system. So that's that graph that I kind of showed, which is showing across the entire data center being able to move resources between the frameworks. Okay. Okay, so it's Twitter circa 2010. Folks were thinking, hey, I really want to do better than this. I want a cluster manager. So what is a cluster manager? Well, cluster manager really provides a level of indirection in between the hardware resources, the machines that are actually running, and the applications or jobs that are running on top. Okay, so instead of a human going and manually scheduling and saying, hey, I'm going to run my stuff like this, there's this piece of software that's in between all these applications that are being run and the machines and the resources that are actually available. Okay, that's a cluster manager. So why in circa 2010 was Twitter saying, hey, I want a cluster manager? Mostly because there were a lot of ex-Googlers at Twitter, and they'd come from Google, where they'd used a cluster manager there called Borg. Okay, so they were saying, hey, I want Borg. This is really what I want. Okay, and that's why Mesos was actually introduced. Mesos was a project that actually started at Berkeley, and it's a modern general-purpose cluster manager, something that's not just focused on batch scheduling. And I'm going to dive into a little bit what I mean when I say something that's not just focused on batch scheduling. For those of you that have used cluster manager in the past, a lot of you have used them specifically for batch scheduling. Okay, so if Google was kind of the OGs of cluster management is a very hot topic right now. And if they were kind of the OGs, the real OGs were the academics, right? So cluster management has existed for a while, and the reason was kind of there was different software that academics were trying to run versus industry. And when I say academics, I also mean government labs. There's lots of other organizations as well. But this is where a lot of the work really happened. So there was different software between what was happening in academia versus industry. So in industry, we were trying to run web services. In academia, a lot of what people were trying to run, especially government labs, were things like MPI, large simulations, doing things like determining what the weather pattern is going to look like, so forth and so on. Okay? And for a lot of these folks, they were also at much different scale. So industry tended to be at sort of the tens of machines, whereas academia was already at the hundreds of machines because they wanted to use as many resources as possible to actually compute these simulations. Okay? And the cluster managers that academia was actually using were things like PBS, Portable Batch System. PBS was actually introduced in 1991, so it's very old. It's not that old, but it's pretty old in computer science terms. Other schedulers like Torque, Sun Grid Engine, which I think is now called Oracle Grid Engine. In industry, the kind of cluster management that was happening was either raw SSH, using things like Puppet Chef, CAP, and Ansible. Okay? Now, the scales are really converging. For industry, organizations are not running at the tens of machines, they're into the hundreds of thousands of machines, the same in academia. Okay? And these cluster managers that were really focused on batch computation, industry is trying to run more than just batch computation. They're trying to run other kinds of computations as well. And that's why we really introduced Mesos. So it's a general purpose cluster manager, but focused on not just batch computations, but other kinds of computations you're trying to run as well. So batch, including service-like computations, request response services, these distributed systems I was talking about earlier, storage-like computations, distributed systems that are databases, streaming-like computations, things like Storm, so forth and so on. Okay, and I'm going to dive in a little bit more detail of what that actually looks like in a Mesos world. So instead of humans actually deciding when they want to run these different kinds of computations, what machines are going to use, the cluster manager acts as the level of indirection, and these individual things themselves act as the schedulers that actually decide what computations they want to run across which machines or resources are available in the data center. So we actually call these things schedulers in the Mesos world. Okay? Okay. So what Mesos is really doing from 10,000 feet is it's saying, okay, we're going to have these components called schedulers communicating with this level of indirection, this cluster manager called the Mesos master, which manages all of the machines that actually exist in the data center. Okay? And the primary role of Mesos ends up being the thing that's really responsible for the allocation and the reallocation of resources across these schedulers. Okay? So going back to kind of the static partitioning world that I was talking about earlier, imagine if we'd started with a static partition that looked something like this. We had two different types of things we're running, let's say Hadoop and Rails, and we've given so many resources to Rails and so many resources to Hadoop. So in the Mesos-like world, we can readdress those challenges that I talked about earlier, things like, say, failures in maintenance, because if a machine were to fail, or if that machine were to actually go offline because there was a maintenance event, the machine goes away, very, very easily, this cluster manager in between can find available resources, reallocate those available resources to the service that was trying to run, so it can continue to serve whatever it's trying to do. Okay? The same thing is true of for the utilization challenge. It's very, very easy as resources come and go to basically be able to move the allocations back and forth very dynamically based on who actually needs those resources. Okay? Okay. All right. So the model that Mesos is really providing is what we call two-level scheduling. Okay? And Mesos was really influenced by operating system-supported user space scheduling and concepts around scheduler activation. And in this way, we think of Mesos less like a cluster manager and much more like an operating system kernel. Okay? And to kind of dive into that, I really want to talk about the level of abstraction that Mesos really fits and how it differs from other things that exist in our technology stack today. Okay? So the Mesos level of abstraction is really about being able to build and run these distributed systems or services where the abstraction is resources. It's not exposing the machines, it's exposing resources with fault domains of where you can actually run computations and tasks. Okay? Mesos is at a higher level of abstraction than something like infrastructure as a service, where the abstraction that's really being provided with infrastructure as a service is to provision and manage machines. Okay? So the abstraction there is, hey, I want to get more machines from machines. That's the function, right? And at the same time, Mesos is at a lower level of abstraction than something like platform as a service, okay? Where the abstraction there is really about being able to deploy and manage applications and services. Okay? So different levels of abstraction across the stack. What's really interesting about Mesos, though, is you can very easily build something like a PaaS directly on top of Mesos. Okay? And I'm going to talk a little bit later about something that we've done like that called Marathon. Okay? And at the same time, you can run Mesos directly on something like OpenStack, EC2, and infrastructure as a service. But what it does is it really provides this level of abstraction on top of something like the infrastructure as a service. So at the same time of running on something like OpenStack, you can also run it directly on bare metal. Okay? So this is really nice for a lot of people because they can have a single level of indirection where you can build your entire operations on top of, which you can either be running in a private data center or in the cloud, and you don't have to care about either one. Okay? It's just machines that you're getting, whether you're getting those machines from Google Compute, Azure, Amazon, or those machines are actual physical machines, it doesn't matter. Your level of abstraction is a little bit higher. It's Mesos. Okay? And in that way, we really think again of Mesos as this data center kernel where you build these things called schedulers on top of Mesos, and Mesos ends up providing this common functionality for all the schedulers to run across the machines, whether those machines are bare metal machines or virtual machines in the cloud. Okay? Okay, so the whole point of this section was to talk about, okay, well, how should we actually run data center applications? So let's get back to that point, okay? Let's get back to how should we actually run data center. So returning to this picture that I showed earlier, which is a very small snippet of what Twitter's distributed system looks like, one of the things we can really focus on here is we can say, well, we've got a bunch of these microservices in the center, right? And all these microservices have one thing in common. There's these stateful services that we can just schedule anywhere in the data center, okay? And so getting back to this picture that I showed earlier about the different kinds of computations that you could support running on top of Mesos, we can build a service scheduler that's focused on running nothing more than those kinds of microservices, okay? So a service scheduler kind of looks like a PaaS. Okay, it's kind of like a PaaS. It's this idea of being able to orchestrate services on top of Mesos. Okay, but I want to really break down what it looks like in the Mesos ecosystem. Okay, so the way a service scheduler really works is it communicates with Mesos in order to schedule these services across the data center, depending on the constraints that it actually has to run those services. Okay, what it provides as an abstraction, kind of like what a PaaS provides as an abstraction, is the notion of orchestration. Of being able to let a human, a developer or an operator, specify declaratively that they want to run this service or this collection of services that looks like this, passing it to the service scheduler, which is then responsible for scheduling that through Mesos across the data center. Okay? And this is a really important distinction. It's the most important distinction when it comes to Mesos versus other cluster management-like things that are out there today. Okay? Okay, so I want to dive in what this orchestration really looks like with a service scheduler. The service scheduler I want to focus on is Marathon. It's one of the ones that we actually built at Mesosphere. Okay? So returning to those three considerations that I mentioned at the very beginning, configuration and package management, deployment, and service discovery, what does that look like with Marathon? Okay, so I'm going to walk through each one. Okay, so the first one, configuration and package management. So what developers can do is they can bundle their individual services really in two ways. One is they can either bundle them as tarballs, gzips, static binaries if you've got C, C++, Go, whatever it is, that they bundle that up, or using a Docker image, a Docker container, they bundle that up and then they store that someplace. So that's either someplace like HDFS if it's a tarball, S3 if you're on AWS, the Docker registry if you're using Docker. Okay? Then a developer can go ahead and they can say, all right, now I've bundled up my bits. Now I'm going to describe how I want my bits to actually get run. I do that using JSON. And then once I've done that using JSON, I submit my services that I want to run to Marathon via REST. Okay? So here's kind of an example Docker JSON. This is pretty minimal. This is just describing a single instance that should be run based on the libmesos Ubuntu Docker image with minimal amounts of CPU. And all it does is every 10 seconds it prints out the date. So pretty simple service, mini microservice that we run. Okay? Once that gets running, the last consideration that we really need to deal with is service discovery. So we walk through configuration, package management, deployment, and now finally service discovery. Okay. So there's a couple different ways of actually doing service discovery. I'm going to talk about 2.5, and then move on. So at Twitter, we actually used Zookeeper for doing all of our service discovery. The way that looked like is when a service got launched via Mesos. That service got registered in Zookeeper in what we called server sets. Our applications actually use server sets for communicating. So when some other application wanted to find the first application that got launched, it would communicate first with Zookeeper and it would say, hey, I'm looking for this service. It would tell the service where it was located, and then it would connect to the first service and say, great, I found you, I'm trying to communicate with you. If this looks a lot like DNS, it is because it is effectively DNS. It's just a DNS that was rewritten for this modern dynamic cloud architecture. Okay? There's been a lot of service discovery alternatives that have been introduced in Mesos clusters. A couple that one that I really want to highlight here is the HA proxy approach. So it looks very similar. A task gets launched on a machine. HA proxy gets updated with the new location for the service. The biggest difference here now is rather than a service finding out where the service is and then connecting directly with it, it communicates through HA proxy as a proxy. Okay? So it's an extra hop. You got to go through HA proxy to actually do the communication. There's a bunch of wins for that. The biggest win for that is that you can use a bunch of existing services that you already have to communicate with your services that are running in your data center. With the Zookeeper approach, you pretty much have to get everybody to speak that, or what you end up doing is you go and build a proxy which speaks Zookeeper. So either way, you have a proxy. Okay? Okay. So one of the things that's really important here is that there's many different ways of doing orchestration on top of Mesos. Okay? The other one that I want to highlight is using Kubernetes to do orchestration on top of Mesos. It looks pretty similar to the Marathon world, the 3 steps: configuration, package management, deployment, and service discovery. In this case, configuration and package management is via Docker. Deployment, you still end up writing a bunch of JSON. You put that in a JSON spec. You submit that to Kubernetes. That then communicates with Mesos to actually schedule the containers or the pods across the data center. Okay? In this case, service discovery is a little bit different. Kubernetes has proxies that get set up that handle a lot of the service discovery for you, but not everything. If you're running outside of Kubernetes, you still have to solve that problem yourself. Okay? Okay, so this starts to get to one of the really interesting value propositions of Mesos and why we built Mesos the way we did. And that's because, I just mentioned there were 2 different schedulers that you could use to actually orchestrate some of your services. And you can actually run them at the same time on the same cluster. Okay? So there's no reason why you can't say, hey, I want to use Marathon to run some things. I might want to use Kubernetes to run other things. Okay? And there's many other schedulers that you run on Mesos at the same time. And I'm going to talk a little bit more about some of them in a few slides. Okay? One of the really interesting things about this model, though, is you can also run multiple of the same schedulers at the same time. So you can run multiple Kubernetes at the same time. So why would somebody want to run multiple Kubernetes at the same time? Well, if you've got one Kubernetes, which is your production Kubernetes, it's running version 0.8.2, and you also want to try out a new version of Kubernetes, you want to see that it's working well before you upgrade and move everything over, you can run version 0.9.0. And I don't know the latest versions of Kubernetes. I think they're somewhere close to here. But in January, there was 0.82 and 0.90. I guess it's been a while since then. Okay, all right. So I kind of want to move into the last part of the presentation, which is if that's how we can run a lot of our data center applications, how should we really be building our data center applications? And I want to give the caveat that for a lot of people out there that are using Mesos or that have heard of Mesos, most people won't actually be building new data center or distributed systems, but Mesos was specifically designed to support that. Okay? Most people will find that using something like Kubernetes on top of Mesos or Marathon on top of Mesos or some of the other schedulers that exist, there's Singularity that HubSpot built. You're going to hear later this afternoon from some work that was built at Netflix, although I don't think it's open sourced. Not yet, it's not open source. So there's a whole bunch of different things that you can run. For some people, they'll just want to use that very one thing. For other people, they actually want to use Mesos to not just run some existing services, but to be able to actually build new distributed systems, new data center applications. And that's what I want to talk about in the last part of this presentation. Okay? It's one of the parts that is the most exciting to me about the actual system itself. Okay? All right, so when you think about distributed systems developers, the kind of things that they really think about when they're building a new distributed system is stuff like this. They want to figure out how they want to do leader election. They want to figure out how they want to deal with some of their states. You know, they have some working set of data. They have to do task management. When I launch a task, which machine am I going to put it on? Which tasks are running where? They want to do some kind of machine management. When those machines fail, what should I do? So forth and so on. Most distributed systems developers all end up doing a collection of these things every time that they build a new distributed system. Okay? Operators of distributed systems have a slightly different set of tasks that they do with. Some of them overlap. Like they want to care about things like, well, what happens if a task or machine fails? If I deployed some distributed system to be running on a particular machine and that machine fails, what should I do? You know, what happens when more resources or tasks are actually needed? Does everything scale proportionally? Do I need to set some configuration of my distributed system in a particular way so that things work the best way possible? Okay, and like I mentioned, there's some things that are common across both operators and developers, but there's really two camps of people that are simultaneously effectively being distributed systems developers. The ones that are actually building the distributed systems in the first place, and the ones that are actually deploying and operating those distributed systems, and all the Python and glue code and everything else that they end up running to actually make those distributed systems work. Okay? I've been one of those people for a long time, and I'm sure other of you have also been those people as well. Okay? From the distributed systems developer's perspective, everybody keeps reinventing the wheel. Right? Everybody is re-implementing some kind of leader election. Everybody is re-implementing how they're going to launch tasks on different machines. Everybody is re-implementing how they're going to decide whether or not a machine has been partitioned away and should be shut down. Everyone keeps doing that. Just like in the original days of running on personal computers, everybody was re-implementing their own memory management. Okay? From the ops perspective, the distributed systems that we as developers throw over the wall to operators to run is a total nightmare. Okay, it's a user experience nightmare. It's so bad that there's a whole cottage industry of books about how to run these distributed systems. Right? There's, you know, how to run Hadoop, how to run MySQL. I picked on MySQL twice because that's the one that I've actually spent a bunch of time operating. And they're experts at these things and they do them well, but a lot of people still have to spend a lot of time doing this. Okay? So there's kind of two big questions that really drove the evolution of Mesos, which was, why does every single distributed system have to implement the same things over and over and over again? Right? And the second one is, why can't we build distributed systems that actually can incorporate and automate operations? Why are there these two people, one that are building distributed systems and other ones that are actually writing code to manage and operate those distributed systems? Why aren't they the same people? Okay? So the thesis here, and one of the reasons why we built Mesos is that we really need a common abstraction layer upon which all these distributed systems can be built. Okay? And this abstraction layer, these distributed systems, they really need to be built with this concept of a scheduler, so that the scheduler can actually be responsible for automating a lot of these tasks, these the operational tasks. Okay, so what Mesos is in a nutshell, describing it another way, is it's really a distributed system for running. That's kind of what I talked about earlier in the presentation, how you run things, but also for building other distributed systems. A distributed system for building other distributed systems, okay? And even more so to the point, that's really why we think of this thing as a distributed systems kernel or a data center kernel. Okay, so diving in, I showed this picture before about the schedulers actually communicating with the masters. What that communication is a syscall-like API that gets exposed up to the actual distributed systems that are running for doing things like launching my tasks, finding out when my tasks have finished, finding out when my tasks have been partitioned away, finding out if my tasks have terminated abruptly, dealing with things like maintenance, which I'm going to talk about in a second. Okay? And by putting Mesos here and providing this syscall-like API, we're able to provide a lot of the common functionality that most distributed systems end up re-implementing in one place. Okay? We can do it there, we can harden it, we can make it work really, really well. Not everybody actually has to re-implement it and suffer through all the bugs that they inevitably suffer through each time. Okay? And then at the same time, we can run multiple of these things at the same time, multiple distributed systems, so we can more effectively share the resources in the data center. Okay? So why would you want to build a distributed system against something like Mesos? Well, first, as I mentioned earlier, because you can really abstract away the hardware underneath. It doesn't matter if you're running on the cloud. It doesn't matter if you're running on bare metal. It doesn't matter. This is your API. You're using this API. It's an open API. It's not a proprietary API coming from a cloud provider. You can build against that. You can run it across any cloud provider that you'd like. Okay? And then also because you can start to leverage a lot of these primitives that you don't have to re-implement yourself. Okay? So Mesos as a data center kernel provides a lot of these primitives. Things are being added all the time. Things like concepts of principals, users, and roles, advanced sharing and allocation algorithms, high availability even during upgrades. When you upgrade Mesos, you can keep everything running. Doing things like resource monitoring, dealing with preemption and revocation, doing things like volume management, doing things like reservations. And this last one, reservations, I want to talk about for a little bit because it ends up exposing some primitives that are tremendously valuable for people that are building new distributed systems on top. So to be able to do something like maintenance in Mesos, if you wanted to run a distributed system like HDFS on top, you can actually leverage the primitives from Mesos for Mesos to be able to tell something like HDFS, hey, this machine is currently going down for reboot. Or this machine is currently going down for shutdown forever. Other things that a distributed system typically doesn't have access to, and therefore it can't do smart things about. So a human otherwise has to come up and say, oh, I'm going to do maintenance on this machine, which means I need to go somehow update HDFS or reconfigure HDFS or whatever it is I need to do. A human gets involved, has to actually deal with that. Wouldn't it be better if the software could just say to the distributed system that's running itself, hey, this machine's going down for reboot, you should do what you need to do because you've got data on this machine or you don't have data on this machine, you need to have more instances running, whatever it is. Okay? So that's really the API that Mesos is trying to provide to these distributed systems, which makes it a candidate for running really sophisticated things like a distributed file system, right? And most of the other cluster managers out there, you wouldn't want to run a distributed file system in them because they just don't have any mechanism of dealing with these kinds of issues. Okay? All right, so there's a lot of stuff in a kernel. There's especially a lot of stuff in a data center kernel. I'm skipping so much stuff that's actually in this stuff. I kind of wanted to give a high-level overview talk. And I just wanted to mention a few things. There's been a bunch of these distributed systems that have been built directly on top of Mesos. Spark, Aurora, which is another one of these service-like schedulers. Marathon, Cronus, which I'm going to mention in just a second. We've also ported a whole bunch of systems to Mesos as well. Hadoop, Storm, Jenkins, HDFS. There's been a bunch of others. We also have a bunch of adopters of the software as well. There's a lot more. I'm just mentioning a couple of them. Please, it's at 2:30. When's your talk? 4 o'clock. At 4 o'clock, there's going to be a talk from Netflix talking about how they actually use Mesos as well. So please come and see that. It's not here, right? It's in another room. Salon A. OK, great. All right. So I've just got a few more slides. Let me conclude, and then I'm happy to take questions. So the data center is really just another form factor. Like a laptop is a form factor. An iPad is a form factor. Our phones are form factors. The supercomputer was a form factor. Why can't we run applications on our data centers just like we run applications on our phones? I'd much rather manage and run my applications and make them look something like this across the data center than the way a lot of us typically do it today. The data center really needs something like an operating system. Okay? So the desktop computer and operating system, we got a lot more resources. The servers still had operating system. Supercomputers had operating system. Phones have operating system. The data center really needs something like an operating system that's managing all these resources. Okay? So with Mesos, what we've really tried to build is a data center kernel that's doing a lot of the functionality that most distributed systems end up re-implementing. People shouldn't be reinventing the wheel. They should be leveraging things out there. And what we're trying to do at Mesosphere is really build something that we're calling the data center operating system. It's taking Apache Mesos, which is the open source kernel, and putting a lot of other software, most of which is open source, around Mesos to provide the entire experience of an operating system. So this includes things like a CLI, a graphical user interface, repository for frameworks and apps that are actually that are also being run. Okay, so what's all in kind of a data center operating system? Well, we're making sure that something like Cronus exists. So Cronus is one of these schedulers that runs on top. What is it responsible for? It's kind of like the cron for the data center operating system. We also have Marathon. I mentioned Marathon earlier when I was talking about orchestration. It's really kind of the init for the data center operating system. And again, as I mentioned, you can swap it out for something like Kubernetes or Aurora or Singularity, just like you can choose between Chrome or Firefox or Internet Explorer or any of the web browsers that you actually choose to use. Okay, just about running schedulers. Okay, so I've spoken for 45 minutes and 59 seconds, 46 minutes. I wanted to speak for 45 minutes. So I'll stop here. I'll take some questions from the audience. And we'll use, OK.
So in the example where we're talking about deploying Docker containers and you had volume mounts, like what part of Mesosphere lets you actually get that data on the host, set the hosts up so that they can run Docker so that your files are there to be volume mounted? Okay, so it's a great question. So there's a couple of different mechanisms right now. There is a way of actually specifying artifacts through URIs that when you go to launch something, you can tell Marathon, hey, these are the artifacts that I actually want to have on this machine. And then Mesos will actually pull those things down. Okay? More likely, the volume management stuff in particular is designed not for copying data in initially, but for letting something like an HDFS come up and make sure that it has a long-lived volume that's always going to persist on the machine. Okay, so it comes up, it's initially empty. Maybe it gets data right away because it's part of the existing HDFS and there's more data that's going to get replicated there. Or the same thing with Cassandra or MySQL or any other service. And that's how it gets populated. But there are mechanisms of explicitly saying, pull this down to actually run my application. Beyond just a Docker image or a tarball or anything else, you can also pull down any other URIs.
Is that also how state is managed? And what about when nodes fail? Is there any support for checkpointing or migration or anything like that?
Yeah, so we don't provide any explicit state management or checkpoint migration or anything like that. What we provide is primitives back to the schedulers that are running so they can implement those things themselves, right? So the example I was giving, the way in which you do something like maintenance is HDFS. An operator can go in and they can say, hey, I want to do maintenance. I want this collection of machines to go down for reboot at this period of time. And kind of the example that I give when I talk to most people is, think about when you're working on like a shared university computer or something like that. And the operator of that computer wanted to do some maintenance on it, and everybody got a wall message that was like, hey, this machine's going down for reboot at this period of time. You should probably clean up your data and get off, right? That's the equivalent of the primitive that gets exposed from Mesos up to these schedulers, where then they can do whatever's the best thing for them, okay? So for something like HDFS, they could find out, hey, these machines are going down for reboot for 10 minutes because it's a kernel upgrade. I'm actually going to do nothing because when the machines come back online, I'm going to have my data. I'm going to be able to do something. Oh, hey, this machine's going down forever. Okay, it's going down at this period of time. I want to start re-replicating my data as quickly as possible because I want to make sure that I have at least 3 replicas of all the data, so forth and so on. So the primitives are exposed up to the schedulers for them to actually then take advantage of however is best for that application. And I just used HDFS a bunch as the example.
I guess my question is, where I work, we have a Spark cluster, and we were sort of debating this question of using Yarn or using Mesos. I was wondering if you could talk a little bit about contrary and contrast and philosophy differences going one way or the other.
Sure. It's a great question. When we first built Mesos, Spark was the very first distributed system we actually built on top. It was about 1,000 lines of code, and it did a lot of the core functionality that it still does today, and I think it's like 100,000 lines today or something like that. So that's kind of the value of being able to build a distributed system on top of something like Mesos. That's just the history, so everyone knows that. Now, the direction that Mesos then went in was a company like Twitter that wanted to use Mesos not just for running analytics, but for actually running long-lived critical services, things like Memcache, things like databases, Redis, the actual services that you hit when you are tweeting, all those types of things, right? So we spent a lot of time and effort actually building into Mesos functionality to enable that to be the case, to enable to scale to many, many machines, to enable us to have high availability across all types of failures, when schedulers fail on top, when the masters themselves fail, when the slave processes themselves fail. On each machine, we run a little agent process, and it's even the case that that agent process can shut down, and all of the containers that we've launched will continue to run. Why is this really critical? Well, it's critical if you want to, say, be able to upgrade a Mesos cluster without causing any downtime to your apps. And that's kind of one of the things a lot of people forget to think about upgrading of the cluster manager itself, but it's really, really critical, right? So a lot of those features were built that make it so that if you're trying to run more than just analytics, my recommendation is that you'd use something like Mesos instead of Yarn, because those are not features that exist in Yarn. There's a couple other differences that I'll throw out there. Yarn is written in Java, Mesos is written in C++. There's 2 reasons why that could affect you. One, if you want to contribute to the project, your organization may or may not, and then the other one is, as you start to get to larger scale, giving a 1 gigabyte heap or so for each of the Yarn agents actually adds up. And so it's, again, from a resource utilization perspective, it's something we really focused on for Mesos. Let's see. There's other fundamental things as well. I have slides for all of the answers that I'm giving from other presentations, so feel free to come chat with me otherwords. There's the way we actually do resource allocation in Mesos is different. It's more optimistic. And then finally, the way in which we actually do resource fair sharing, resource isolation on the individual machines is much more fine-grained as well. So there are a bunch of little differences there. The biggest one, though, is that we spend a lot of time and energy, and we continue to spend a lot of time and energy thinking about how we can run more than just analytics. What are the primitives we need to build to run databases? Right? That's kind of the holy grail. When you run databases really effectively on cluster managers like this, that's a big deal. And we're not done. I mentioned these maintenance primitives that somebody just asked about. We're continuing to add more and more of these primitives in and grow the project in that way. OK, other questions? That was a great question. Yeah. Wait for the mic.
So I have seen in all of your talks that one of the things that that is very clear is that Mesos was designed to run multiple schedulers.
Yeah.
And what if like somebody writes a bad scheduler, which is sort of like hogging most resources, or if I'm a shop and I just downloaded a scheduler that someone wrote,
Yeah.
and I'm hooking it onto my main Mesos cluster.
Yeah.
10 months ago or 11 months ago, like I've seen like side effects like this. Maybe things have become better now, but where is that direction going towards, like of supporting like multiple schedulers in a much nicer manner?
It's a great question. So what's existed in Mesos thus far are the concepts of static reservations. Static reservations are effectively reintroducing static partitioning into a cluster, into a cluster manager, where the whole point was to get away from static partitioning because of all the issues. Okay? We introduced them because it helped us deal with a lot of these rogue frameworks that would take up a bunch of resources when we didn't have the right ACLs in place or other things like that. Okay? The direction we're moving to is actually more around dynamic reservations, stronger preemption, quotas. Those are kind of the three things. So then there's a lot of work that's actually happening on that right now. The dynamic reservations work enables us to basically change the reservations dynamically as the cluster is running. So you can give the strong guarantees, but not in a way in which when machines actually fail, you don't make sure that those frameworks, those schedulers can't get the necessary resources allocated to them. That hooks into quota because we want to guarantee that certain roles that are actually running the cluster get at least so many resources. And it hooks into preemption because, yes, we're going to have to revoke some resources from some frameworks that shouldn't have those resources in order to guarantee the quotas and let these people create their dynamic reservations. So those are all very, very hot, active pieces of the project right now. And I expect to see them, most of them land very soon. We just did a 0.22 release, which had some of these to start to get implemented, and I think 0.23 will have all of dynamic reservations and preemption, and maybe 0.24 will also have some of the other aspects as well. Yeah, and to be clear, I just mentioned releases, and they start with a 0 instead of a 1, and some people are probably thinking, whoa, why does stuff start with a 0 instead of a 1? Is this not production software? We definitely consider this production software. It's run in production at a lot of organizations. The reason why we have not done a 1.0 release is because one of the other things we're working on right now is a revised API for these schedulers themselves. As more and more people are building schedulers, we've gotten a lot more experience of what that syscall-like API should look like. And so we want to do that before we cut a 1.0 release, just to be generous to all of our developers, and rather than cut a 1.0 and then immediately deprecate and go to 2.0. The existing API, for those of you that are using it, is going to exist for a long time, forever, actually. We'll just keep it around forever. But all the code paths will go through the new API. And so that should also be very, very soon. Any other questions?
Kind of a specific question, but I saw that the like the HDFS example that you described online, that it's under the Mesosphere GitHub repository.
Yep.
And on your timeline, I think it was like 2014. Like what's the like level of maturity for the
Alpha.
HDFS? Okay.
The HDFS framework, I would say, is alpha. There's a couple of companies that are working on it with us. We're trying to grow that community in its own right. We might actually merge it in a bit with the Myriad community that was created. Myriad is actually running Yarn on Mesos, and I should have actually mentioned that when the Yarn question came up. We actually did make it so you can run Yarn directly on Mesos. So for people that do want to run Yarn for particular things, they can run it directly on Mesos. Why might you want to do that? Well, if you are running some of the other Mesos frameworks where you want some of the other guarantees that Mesos provides, but you still want to run Yarn, you could run it on the same cluster. So we might merge those two, but right now it's alpha. Our goal is to roll it into beta as quickly as possible. Okay, it's 11:29, so thanks very much for coming.